Hello, everyone, and welcome to our Chapter 11 review. Now, this Chapter 11 was probably introduced in the first semester of organic chemistry, but here I wanted to start off with this Chapter 11 specifically because it focuses on one really important aspect of organic chemistry, and that is synthesis. I want to take the time to tell you what do you need to know, how do we attempt synthesis problems, and what would you expect to know from the first semester of organic chemistry now that we're past it and moved on to second semester? Well, some of the really important reactions that we saw last semester were our addition, elimination, and our substitution reactions. I know what you're thinking, Lauren, that was all of them. But what's really important is those statements of what are we doing here? Are we adding something to a pi bond? Are we eliminating something to create a pi bond? Or are we substituting a sigma bond for another sigma bond? So here we go. This is what we need to start thinking about. How do we approach a synthesis problem? When I give you a fill in the blank and a reactant and product and I say, tell me how you do it, there are two questions that we want to always ask ourselves. Is the carbon skeleton changing? Are we gaining or losing carbons? I cannot emphasize to you more how important it is to count those carbons. It might seem fundamental, it might seem silly, it might seem way out there, whatever it might feel. I really want to strive to normalizing the counting of our carbons on our reactants and comparing it to the carbon count on our products. The second thing I want to be asking myself is there a change in the identity or the location of the functional group? And we need to be as specific as possible. The more specific you are in describing those molecules, the ones given, the reactant and the product, the better you will be able to recall the reaction that is required. So practicing is always important. However, answering these two questions prior to your practice, prior to starting to drum through all of those notes and see what's going on, you need to ask these questions. And that's only achieved by looking at the practice problem very intimately. So in solving a synthesis problem, or what we call providing the reagents, fill in the blank, it can be as straightforward as only one step. Your job is, again, to assess what do we need to do. So I would look at this first problem, and I have my reactant over here on the left, also called the starting material, right? SM, starting material, what you're given. And then I have my product, my desired molecule on the right-hand side. So I would look at this and say, okay, let's count my carbons. That's the first thing, right? 1, 2, 3, 4. Got to count them and try to count on the right and the left in a very similar manner to try and be able to match up your carbon chain, right? What I've noticed here is that no, there is no change in the carbon count, all right? What I have done is I have removed a pi bond. I'm starting with an alkene, a carbon-carbon double bond, and I am creating a vicinal dihalide. Now, we may be a little rusty, and we may be like, whoa, Lauren, that was a lot of words that I don't remember. Do you see two halogens? That's all I need you to be able to note is you see two halogens adjacent to each other, next door, all right, on carbons that are neighbors. And so that is our vicinal dihalide functional group. Now, we've looked and we've identified carbon count didn't change. We've identified that we had an alkene and now we don't. We have a vicinal dihalide. What did we do? Well, our double bond between carbon 2 and 4 broke and became two new single bonds or sigma bonds on carbon 2 and 4 connecting to bromines. All right, this is an addition reaction. Now, addition reactions, we started off in chapter 8 with alkenes and chapter 9 with alkynes, the double bond and the triple bond respectively. Now, when we look at this problem, we have to be able to remember the reagents necessary to add two bromines. Well, for us, hopefully, we can recall the addition reaction of halogenation, adding Br2 across the pi bond. Now, in order to tackle all of these syntheses, single step or multi-step, what's really important is mastering all of the reagents one at a time. I highly recommend referencing the reactions you may know chart from our first semester organic chemistry course so that you can recall most of the reactions that are important. Now, sometimes in the textbook, a solvent is written underneath this. Br2 is the main reactant that we would have as our reagent here over the reaction arrow. Sometimes we'll see CH2Cl2 or CCl4. These are polar aprotic solvents. They do not have a polar proton on them. They're not water. They just act as a volume enhancer for the reaction. If you forget to write them, I'm not going to cry. It's no big deal. But if you see it in the textbook or if you see it on a worksheet, just know it's a solvent. It doesn't do anything except for assist in this addition reaction. Not in the mechanism. It's not in the product. So don't worry too much about it. Now, for those functional group transformations, I want to spend some time on this two-step synthesis strategy that we've seen from previous chapters, moving the functional group from one carbon to the other. Now, imagine that we don't see this middle alkene section. That's going to be really, really helpful for us, though, to be able to remember if we're counting our carbons and we see that the carbons stay the exact same, and technically the functional group stays the exact same, this is where I want us to be extremely specific. I start over here with an alkyl halide, and I'm ending with an alkyl halide. But let's be a little bit more specific on carbon 2 versus carbon 3. On a less substituted carbon to a more substituted carbon. The more specific you can be in your descriptions, the better you will be able to recall the steps necessary in order to convert the alkyl halide starting material to the desired alkyl halide product. Now for this one, we are going through that in between alkene. And the reason why we are doing that is because once we start thinking about, well, how do I move a functional group? Well, I need to remove the bromine on carbon number 2. I need to put or add the bromine on carbon number 3. And so by doing that, we are essentially doing an elimination followed by an addition. All right. Here's all the reactions we know. This can get a little daunting, but I want us to be able to predict. Now, again, I'm going to start over here on the left with counting carbons. We're just doing our predictions here. How can I eliminate a bromine? Well, it was with a reactive base. This is a good leaving group. And I'm going to need a base. Can leave or be eliminated with a base. Our best bases that we had that did the job were an oxygen minus, a nitrogen, such as DBN, DBU, or sodium hydride, H minus. So we have a couple of options here, but let's recall that lovely E2 reaction where we have an alpha carbon, carbon number 2, that has a leaving group, and there are possible betas, beta 1 and what I'll call beta 3 over on the other side. We have 2 betas, which means we have 2 positions where the alkene can be formed. Now, We know that the size of the base of an E2 reaction will help predict the location of our major product alkene. Sodium ethoxide is a Zaitsev base, meaning that it will pull off the proton on the more substituted beta to produce the more substituted alkene, or what we call the Zaitsev product. These Zaitsev products are more stable. The more substituted your alkene, the more carbons around it, the more stable the alkene. So this is a tri-substituted alkene right here. There is another option. Tert butoxide is a Hofmann base. The Hofmann base here prefers the less substituted hydrogens. I'm just going to draw one on carbon number 1 there. The reason why it prefers the less substituted, even though that less substituted Hofmann product is not as stable as the Zaitsev, is because of steric hindrance, that big bulkiness that increases the energy of the transition state and makes the reaction super, super slow. We don't want steric hindrance when we're dealing with something like tert butoxide. It's big, it's bulky, it's carrying a lot of baggage, so it's going to pull off the hydrogen that is easiest, least amount of steric hindrance, most available, all right? Now, we see in our counting here that the Zaitsev product is better because, again, remember the idea that that new bromine that we had in our product was on carbon 3. So we need our alkene to be joined to carbon 3, all right? The Hofmann product isn't bad. It's never gonna be the wrong answer. It's not always gonna be the wrong answer, but for this one, it is the wrong answer. It's the bad choice, specifically because we don't wanna hook up carbon 2 to 1, we want 2 to 3. We know, based off of counting the product, we wanna put a halogen on carbon 3. Now, how do we put a halogen on carbon 3? Through the Markovnikov addition of HBr. Markovnikov addition here goes through a carbocation intermediate where the H gets added to carbon 2, the carbocation gets placed on the more substituted carbon 3 to be more stable. And then Br minus can come and finish the addition, all right? Just to put it out there so that we remember our radical reactions, HBr with a peroxide, ROOR, ROR, is our anti-Markovnikov. That doesn't mean that it goes through a less stable intermediate. It means that the order of operation is different, that the bromine gets placed on the less substituted carbon first, and the radical intermediate of this reaction goes on the more substituted center. All right? Good ones to remember. All right, a couple more functional group transformations here. Again, showing you intermediates, showing you the step-by-step analysis so that we can really hone in on these individual reactions first. Now, here's my starting material. Here's a product. We'll call this product number 1 and product number 2. Again, just to see the differences. Let's attempt the first one. My starting material has 1, 2, 3, 4, 5 carbons. My product number 1 also has 5 carbons. Again, no rhyme or reason how I'm counting as long as I'm trying to be consistent. My functional group of my starting material is an alcohol. Let's be very specific. It's a secondary alcohol, meaning that the carbon attached to the alcohol, this one, is a secondary carbon. It has 2 other carbon groups, carbon 1 and 3. All right. Product number 1 is also an alcohol. It is a tertiary alcohol because the carbon it is attached to has 3 other carbons, carbon 2, 4, and 5. So the approach here must be to modify the alcohol from a less substituted position to the more substituted position. Notice we're really describing that a little bit more. The more substituted position. Thinking about Markovnikov addition again. How do I get an alcohol, an oxygen, an OH on the more substituted carbon? So we're still going to see an elimination. Got to get rid of the first alcohol, form the alkene. And then we want to see an addition. And let's be a little bit more specific here. Let's say a Markovnikov addition. If you ever see me write Mark addition, don't be like, who's Mark? What's Mark? What's he doing? Who's he in OChem? I don't know. Markovnikov. All right. Just takes a very long time to write that beautiful Russian name. So elimination of alcohols was not with just a base. All right. There are a couple of different ways that we could do an elimination reaction with an alcohol. The best way possible is the most straightforward, the way that we would not get multiple products. Notice again, this elimination reaction, I'm showing it go through the alkene. That makes most sense, linking carbon 2 to carbon 3, making the pi bond on the Zaitsev position, not carbon 1. So alcohols are not good leaving groups, but we can make them good leaving groups. We need to make that alcohol a good leaving group and then follow it up with our E2 reaction. The best way to make an alcohol a leaving group is by using TSCl, tosyl chloride, and pyridine. Now, tosyl chloride makes that alcohol a tosylate, which is a good leaving group. And then we can follow it up with our small Zaitsev base. Sodium ethoxide is a great one to remember. So notice how we're just changing our elimination slightly based off of our leaving group. Now, once we get that Zaitsev alkene product, now we need to think, how do we do a Markovnikov addition? H3O plus. Markovnikov addition in a Bronsted-Lowry acid, just like HBr before, adds a Br Markovnikov addition-wise. H3O plus is another Bronsted-Lowry acid that adds an alcohol on the more substituted position. Awesome. Let's pop down to our product number 2. Again, going through the alkene and finding out our product number 2 is a primary alcohol, a less substituted position. We got to think, eliminate the alcohol again and add the alcohol to a new position. But again, let's be a little bit more specific. My alkene here is my Hoffman product, and my addition should be anti-Markovnikov, anti-Mark. All right, so again, eliminating an alcohol, make that alcohol a good leaving group, follow it up with a Hoffman base, terpetoxide. Terpetoxide can be written a couple of different ways. We can draw the skeletal structure with the coordinating potassium cation. You can write it how we did before as TBUOK. Many different ways to do it. If you have any questions of, hey, what the heck is that? What did you use? Why did you abbreviate? Yes, organic chemists can be a little lazy, so call me out on it. Make sure you know what I'm writing and make sure you're not questioning that. I really want to make sure that we understand all of the ways to read these organic reagents. Now, recall in our mind, what did we use for an anti-Markovnikov addition of an alcohol? Hopefully, we remember it's a two-step reaction. of hydroboration, oxidation. Nice. Hydroboration oxidation is our anti-Markovnikov because it adds concerted that boron and hydrogen, and boron gets added to the less substituted position, again, because of steric hindrance. All right, with functional group transformations, really important when pi bonds want to move, we just see kind of a little reverse of what we just did. When we want to change the functional group of an alcohol or of a halogen, we eliminate and then add. To change the functional group of a pi bond, we need to do an addition followed by an elimination. And the reason for that is because what we see is that we need to break the pi bond and then reform the pi bond. So the first reaction, the best thing to do is add on a leaving group, right? Because if we know we're going to have to eliminate, we need some sort of a leaving group, which is why we still have the halogen here of the Br. This, remember, is a good leaving group. Lg leaving group. So you can think an E2 mechanism is easy. All right. Now, it's not to say that the alcohol couldn't have happened. We know how to eliminate alcohols, but notice how it was more steps to eliminate an alcohol. In a synthesis, we want to try to condense those. We want to try to get it to be the best way possible, right? And so that's where we want to be able to say, okay, let's go ahead and start thinking of what's my best leaving group? What's my go-to thing to add? Well, a bromine, a halogen, it could be a chlorine, it could be an iodine, but bromine's the nice middle of the road character here in the leaving group category. Now, how we add that bromine is really, really important. If we're trying to get to our final product, again, let's count 1, 2, 3, 4, 5, 6, 7 here on our starting material, and our desired product here, 1, 2, 3, 4, 5, 6, 7. This was our desired product. And the bottom is an alternative route that just shows an alternative product. So to be very careful of what reagents we are using and to try and recall the reaction first. So best thing to think about is if I have two carbons here, carbon 2 and carbon 3, that are different, where do I want the bromine? Well, if carbon 2 still has the pi bond at the end of the day, and notice how carbon 3 doesn't, carbon 3 must have gained a hydrogen, which means that carbon 2 would have gotten my leaving group. And so we have to think Markovnikov addition with HBr. All right. If we wanted to do the alternative route, if we were thinking about carbon 2 gaining the hydrogen and carbon 3 keeping the pi bond, notice how carbon 3 here in our alternative product is the less substituted position. We do know a way to do our anti-Markovnikov. And that's with HBr and ROR, a peroxide. All right. So be very aware of these two ways to add a halogen, add a good leaving group, and make sure you're noting what they do differently so that you can be able to utilize them appropriately. And then the last thing, the elimination. Let's go back up to our desired product. 1, 2, 3, 4, 5, 6, 7. We want that pi bond between carbon 2 and carbon 1, which means carbon 1 must be the beta to my alpha with the leaving group. And if I want that pi bond between 2 and 1, I should note that beta 1 is the less substituted position. And so I would want a Hoffman base. Best Hoffman base to remember, potassium tertbutoxide. Looks like a chicken foot. Nice. On the bottom, Noticing that we are going to add the pi bond between 3 and 4. Again, the less substituted position. Notice how carbon 2 is more substituted than carbon 4. If we want the less substituted carbon to become my beta position, where the double bond shows up between alpha and beta, we'll use the Hofmann base. Awesome. We will definitely practice with a lot of these two-step conversions between alkanes and alkenes, or double bonds and triple bonds and single bonds. All of these lovely functional groups are going to be important to remember how to get there. And we'll do this in class too. But overall, to get to the alkene, we need to add on a functional group. And with an alkane, we're very, very plain. What do we have? What can we use? If you remember chapter 10, it was starting with our alkanes and using radical halogenation. Now, radical bromination, Br2, with heat or light, there's light. You could also use, put it off to the side, Br2 with heat, delta. There's an option for that first step. All right, that puts a halogen on the most substituted position. It's a substitution reaction. There was a hydrogen there, and now there's not. There's a bromine. So overall, substitution. We haven't seen too many of those today. It's always good to remember those radical ones because they can make functionality out of almost nothing. An alkane. Our second step is an elimination reaction. Noticing that this is a Zaitsev elimination. If you need to go back to our Zaitsev idea, the more substituted beta, this one down here, call this beta 1 versus beta 2, right? This is also a beta 1, same one because of symmetry. If we're choosing the secondary carbon, beta 1, the one that has 2 other carbon groups, versus beta 2, which is a primary, sodium ethoxide is a great one to remember. All right. Now, when we want to be able to convert and change those pi bonds, we do need to remember that those transformations to go from the alkyne to the alkene, we can choose H2 with the poisoned Lindlar's catalyst, or sodium and ammonia. All right, Lindlar's catalyst made cis alkenes. Sodium and ammonia, dissolving metal reduction, made trans. If you want to go back through that reaction, check out chapter 9. Now to go from an alkene to an alkyne, this one was a tricky way, going backwards on that bottom left-hand side. We need to make a triple bond by adding 2 leaving groups. Br2, and we'll step this one out and show the intermediates. Br2 adds 2 leaving groups. Ooh. Nice. We need to do the double elimination. The best way to eliminate to make the triple bond was using sodium amide. Now, what that does in step number 2 is it not only makes the triple bond, but if you have a terminal triple bond, it will also do an acid-base reaction. So E2 plus acid-base. Can't stop it. It's so reactive. Sodium amide is such a reactive base. So step 3 here, if you do have that terminal alkyne, if you had a triple bond with an acidic proton on it, you need step number 3 to put that proton right back on. Right, that's a big one. A little bit from chapter 2 or chapter 8. And then the preparation of the alkyne is also revisited in chapter 9. So all of these that we just did in blue and purple, chapter 9. To go from the alkene to the alkane, chapter 8 material, H2, PT, palladium and carbon, platinum, nickel, hydrogen gas with a reactive catalyst. To go backwards from the alkane to the alkene, say that one 10 times fast, the single bond to the double bond, we do what we just did above. Br2 with heat or light, followed by a base. I'll just put sodium ethoxide here. Now, changes in the carbon skeleton. This is something we've seen a lot of functional group transformations right now, but I want to recall our changes in the carbon skeleton. These are the ones where we add or remove carbons to our molecule. So when a synthesis requires that change in the carbon skeleton, you need to be able to remember what reactions add or remove carbons. It's good to make a list. I'm totally into concept mapping, whatever works for you. So here is a review of the reactions that we have done where we have changed the carbon skeletons. Using the alkanide ion, that carbon with the negative charge, specifically it's an sp carbon with a negative charge. Also called the alkanide ion. Check it out in chapter 9 if you don't remember it. What it does is it is a very good nucleophile. Nuke. It is nucleus loving, looking for something positive, right? Nucleophile. Nucleus loving. Oh, Philae. Yeah. Why does it look for something that's positive? Well, what's in a nucleus? Protons. Positively charged things. So it is, as a nucleus, this alkanide ion is looking for something that is delta positive or actually positive charged. When we see our other molecule over here with X, which is most likely a halogen, that is a leaving group. So that means this first blue carbon is the alpha carbon, this alpha carbon being the electrophile, meaning electron loving, electrophilae. Yes, electron loving. It is looking for electrons. Match made in organic chemistry heaven. Oh, so romantic. The nucleophile attacks the electrophile. That carbon can't have 5 bonds though, so it takes what it can and kicks off the best leaving group, making that new bond. Organic chemistry love. This was our SN2 reaction. Nucleophilic substitution by molecular. 2 things coming together in a nucleophilic attack and a loss of leaving group. This is the best way that we know how to add carbons. You add at least 2 carbons. 1, 2. All right. We'll learn a lot more ways to add carbons later on in this semester, but this is a good first start. Now we've also learned ways to remove carbons from a molecule. Ozonolysis is a reaction that is very good at breaking sigma and pi bonds. Noticing here that ozonolysis literally splits the sigma and the pi bond apart and oxidizes those 2 carbons. I'll label them as carbon 1 and 2 here so that we see we make aldehydes or ketones based off of what else is attached to that alkene. This works for alkenes to become aldehydes or ketones. If you have a carbon-carbon triple bond, we'll just write that one down here. And I'll put R. R groups are just carbon groups, right? O3. Water is the workup here, not necessary to do anything else. Carbon 1 and 2 where the alkyne is. get separated and we fully oxidize into carboxylic acids. I'm going to try to draw them similar to how I originally drew them. 1 and 2. If the R group is a hydrogen, then we make CO2, carbon dioxide gas, bubbles out of solution. All right. So again, overall, what we want to be able to see here before we get into some more challenging problems, we want to note the change in the carbon skeleton, gaining or losing carbons. We need to know those gaining or losing reactions. And then we also want to note the change in the location or identity of a functional group. Okay, let's do it. Let's count our carbons. Now count in any way, shape, or form that you want to. I will count left to right for this one. If you want to count right to left, that's a-okay. 1, 2, 3, 4, 5. Now I notice that that starting material is the alkyne. I'm going to call it something a little bit more specific, a terminal alkyne. It means that it's at the end of a carbon chain. There is an acidic proton right there at the end. You don't need to draw it in if you don't want to, but it is good to note. Now 1, 2, 3, 4, 5, 6, 7. I'm adding 2 carbons here. Brilliant. So how do we add 2 carbons? That's a good note. Also, what I want to point out, my functional group change from the alkyne to the transalkene. Notice I said a lot of descriptions here, a lot of descriptions. And it's all of those descriptions that the more you can say, the more you can build up your game plan. Cool. Now, in order to do this, we can start forward. We're going to practice a little retrosynthetic action on the next one, but forward is fine. So what we see here is that we need to do 2 things. We need to add carbons, and we also need to make a transalkene. Well, in order to make a transalkene, I need to add my carbons first. I also see that I start with the alkyne, and I know from my previous notes is that the alkyne with a acidic proton can become the alkynide ion. So that's my first step. I want to deprotonate. I'm going to start labeling these 1, 2, 3, 4, 5 just around the bends so that we can see all the intermediates in the practice. Deprotonate that terminal alkyne, acid-base reaction. All right. Then I want to add my 2 carbons, what I'll call 6 and 7. Well, the best way to do that is to drum up that alkyl halide. We know that the nucleophile I just made in step number 1 means an electrophile. There's that SN2 reaction. You never need to label SN2, but I'm trying to recall when we've seen it. Be careful with drawing out your triple bond. Remember, it's linear. Let's still count our carbons. 1, 2, 3, 4, 5, 6, 7. Beautiful. And then my last step, recalling how to make the transalkene. Now I have an internal triple bond, an internal alkyne. Now I can make this trans with sodium and ammonia. Notice that this is 2 different molecules mixed together. Sodium, the metal, and ammonia, NH3, the base, or the acid, depending on which part you want to look at. Not sodium amide, not what we use in step 1. This is 1 molecule, Na, NH2, no spaces. Na, comma, NH3, 2 molecules, space. All right. So this is a 2-step reaction, but overall it looks like it needs 3 sets of reagents, right? Actually, it's 3 reactions, but it's overall 2 succinct steps. Add the carbons, make an alkene. Retrosynthetic action is one of the most difficult ways to approach synthesis, but the most successful ways. Now, why it's difficult is because we are trying to train our brain to think backwards. And in organic chemistry, I understand that that's difficult. Forward synthesis is fine, but it doesn't work on everything. On more complex problems, we still need to ask the same 2 questions. We still need to analyze the structure of our reactant and our products and be able to talk about this carbon skeleton and the functional groups. But the biggest thing that we have to do is we begin solving the last step of the synthesis first. And the reason we do that is because there is a lot less ways to answer the question, how do I make this, versus what can I do with this? So approaching it by looking at the product is the way that we're going to do this analysis for our last problem together. We'll use retro arrows, which we'll talk about, versus reaction arrows in this sequence. And I want to make sure that we are comfortable with this process. So we're going to try to step it out as much as we can. So here is our transformation. I have my reactant or my starting material here on the left. Here's the product I want to make on the right-hand side. I should still go through and say, okay, is there a change in the carbon skeleton? No, there's not for this one. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. But there is a transformational group change. There is that functional group that has gone from an alcohol to an alkyne, specifically taking the alcohol from carbon 6 and making it into a triple bond between 5 and 6. The position we'll call is not changed. It's unchanged because it still encompasses carbon number 6, right? We're just bringing carbon 5 into the party as well. So work backwards, focus on that last step. What reactions do we know that we can use to make an alkyne? That's a lot easier to answer than what can I do with an alcohol? Well, I can do a bunch of crap with an alcohol, Lauren. What do you mean? Right? There's less ways that we know to make an alkyne, to make the alkyne, than there is to react an alcohol. So yes, this is what we want to focus on backwards. That makes it a little bit uncomfortable, but let's challenge ourselves today to be slightly uncomfortable. There are 3 ways that we know how to make a triple bond. All of them involve the double elimination. And since we're making a terminal alkyne, we'll use a water workup. All right. These are the reagents. Yeah, I know, Lauren, that's great. What do I need to do to use these reagents is have a dihalide. Well, there's 3 options. I'm going to count again my product, 1, 2, 3, 4, 5, 6. I need 2 leaving groups to make a triple bond, yeah? And the best leaving groups I have are halogens. I'm going to use a strong base to do a double elimination and just a water workup because it's a triple bond at the end of my carbon chain. Has that acidic proton right there. Nice. Well, I could put both of the bromines on carbon 5. I could put 1 on 5 and 1 on 6, and I could put both of them on 6. Those are my 3 options. See how those are 3 very specific options with this one reaction. Well, I don't want the bromines to be on the same carbon. I'm going to remove these options and just focus on the vicinal dihalide. This is the only way we know how to make an alkyne from something else. The geminal dihalides where the halogens are on the same carbon. These geminal dihalides are only made from triple bonds. Well, that's not logical. I'm trying to make the triple bond. I probably don't have one earlier. So we would take our vicinal dihalide as the best option here. And then we'll move with this intermediate backwards. So great, we know the last step, right? Notice how we're thinking this way. We start with our product and say, how can this be made from this, right? How do we do that? And those retrosynthetic arrows are the reverse of the reaction arrows. Okay, reaction arrows point to the product. Retro arrows point to the reactant. Okay, so we have our last step. Beautiful. Now we can continue. How do we make this? How do we make a vicinal dihalide? Well, we can do an addition reaction to an alkene. This alkene would need to be between carbon 5 and 6. All right. We know that that addition reaction was Br2 to go from the alkene to our vicinal dihalide. Remember, retro arrows say that the vicinal dihalide, the vicinal dihalide can be made from Br2 with an alkene. So there's our second step backwards. This one's the last. This is second to last. All right, and we're getting closer and closer and closer. We still need to figure out how to get that alcohol to do something, right? But we are getting closer, right? We can see that that last step of converting our alcohol to an alkene. How do we make an alkene from an alcohol is an alkene or an elimination reaction. All right, an alcohol can be dehydrated or eliminated in one of the ways we talked about before. Make it a good leaving group. PYR is a shortcut for pyridine. We have one alpha and only one beta here, so any base will do. Right? Doesn't matter which one you choose, DBN, DBU, anything, right? Then we'll use our Br2. Then we'll use our NaNH2, our sodium amide base, followed by the water workup, because we have a terminal alkyne. All right, overall, we have 1, 2, 3, 4, 5 steps. All right, that's how we would list them out. Let's go ahead and write that. Taking our alcohol, one big long reaction arrow, starting with make that alcohol a good leaving group. Eliminate it. Let's just use sodium ethoxide, that's fine. Br2, the addition reaction, and then our double elimination with our water workup. And that will get us our triple bond. Okay. We should go back and check this step by step forward. That's always a good thing to do. But again, if you're struggling with any of these steps, refer to the individual step, all right? Don't just say, oh, I should practice more synthesis. I don't get synthesis. The best thing to do to practice synthesis is practice the individual forward reactions, the one step, guys, because those are the ones that help us recall or answer these questions of how do I make that? Well, what's happening from my starting material to my product? How do I add a carbon? Those are the most important single straightforward reactions. We'll touch on a couple more in class that are going to be helpful for our transformations, especially the ones that we'll see in subsequent chapters in the second semester organic chemistry. If you have any questions, I will see you in class. Please reach out prior to class or during class for any clarification. Thank you all so much.